Thank you for downloading this podcast from the Forum for Philosophy. Subscribe for weekly discussions of science, culture, politics, and the arts from a philosophical perspective. The Forum is a non-profit organisation, and our events are free and open to all. You can support our work via our website and Facebook page.
Good evening, everyone. Welcome to the LSE, and welcome to this Forum for Philosophy event supported by the British Society for the Philosophy of Science on the topic of black holes. Black holes were, first of all, a theoretical posit. No one could really believe they existed. These places where gravity was so unbelievably strong, nothing could get out, not even light. Then they were an empirical reality, and now for nearly 100 years they've really captured the imagination of not just scientists in physics, but also the wider public, science fiction authors, creative people, trying to think about what on earth these things are and what goes on inside them. The questions we'll be thinking about in this event are: what are black holes? How do we know they exist? How can we know something like this actually exists? How can we even begin to know what happens as one approaches one or even goes inside one? And what can science fiction learn from the science of black holes? And what can science fiction contribute to the science of black holes? To what extent can fiction start to fill the gaps that science is unable to fill? To what extent can science fiction actually be a source of new hypotheses for scientists to then think about and test? And it's a delight to be joined by three panelists who are coming to this topic from very different directions, bringing very different perspectives to bear on these questions. There's Amelie Saintonge, a specialist in extragalactic astrophysics at University College London; Karim Thébault, philosopher of physics from the University of Bristol; and Stephen Baxter, a critically acclaimed science fiction author known for the Xeelee sequence of novels, as well as the Long Earth series with Terry Prachett and the Time Odyssey series with Arthur C. Clarke. And to give you a sense of the format for the event, essentially the panel will focus on a particular topic. We'll talk about it for a bit, and then we'll go to you for your questions on that topic, and then we'll move on to another key theme. And first of all, I'd like to start with you, Amelie, and just this very basic question of what a black hole actually is. I have this kind of basic understanding. Gravity is very strong, light can't get out, very, very dark place. What is a black hole?
Well, I think you've described it pretty much as well as I could put it. Pretty much a black hole is a very, very, very small volume of space that has incredible amount of mass in it, meaning gravity is extremely strong, and as you say, with the key characteristic that light can't escape it. Black holes are not all that mysterious if we put them in the context of stars and how stars form and evolve. We can think of black holes as just one of the possible end products of the normal life cycle of a star. Right? A star normally exists when you sort of have a balance between a lot of nuclear fusion that does a lot of pressure and gravity that wants to push things back in. If at some point gravity is so strong, the star collapses on itself. And in the case of a black hole, that brings all the matter to such high levels of density that you end up with this almost infinite density little lump of material.
So this is one of the ways a star can end, essentially.
That's right.
Collapses in on itself. This may be a very dumb question, but how do we know these things exist? No light gets out.
Yeah,
how do we know
that's a really good question. And so we think now we're quite comfortable saying things like, well, stars can end their lives as black holes, or we say things like most galaxies have a supermassive black hole at their center. Yet, as you say, we can't pick up light directly from the black hole itself. So we need to use...
Do you explain supermassive black holes?
Yeah, so we can think of black holes. They come either in very small size or in extra, extra large. They are either like small or very, very big. There's sort of a massive gap in size in the middle. So we're talking, when I say supermassive black hole, I mean black holes that have above 1 million times the mass of the sun. And those are the gigantic beasts that are found at the centers of most galaxies. So how do we find out about them? That's a really good question. And whether we're talking about the small black holes or the very big ones, it's always a matter of finding their action through gravity onto something else and then inferring their presence. So you have to trust in things like the laws of gravity, general relativity. And then if you see something moving, for example, if we look deep in the center of our own galaxy, we can see stars that are appearing to move. So if you take a picture of the same bit of the sky right at the center of the galaxy over a period of a few years, you can see the stars moving. And if you make a little movie of that, you can see stars zooming around. They trace little elliptical orbits. And that really strongly implies that there is something, right? Normally you go in orbit around something. And in the case of the center of the Milky Way, we can calculate that in that very, very tiny volume of space, there is about 1 million times the mass of the sun. So that's the kind of evidence we have, right? If all the evidence lines up towards there being a black hole.
So it's an inference. We can't see
Absolutely.
them. Obviously, we can't see them, but we have well-established theories of what they would do to nearby objects.
Exactly. And when our observations match these expectations, then we gain some confidence that we are witnessing the influence of a black hole.
Does anything get out? We've got this idea light doesn't get out. Does anything get out?
No.
Well, evaporation, Hawking evaporation.
Well, yeah. So maybe we want to. So at the surface of the black hole, the event horizon,
Right.
we might talk about that. Like, there's the famous Hawking evaporation, but that's not technically material that's coming out of the black hole. It's almost an illusion of sorts.
So stuff can be radiated from the edge.
That's
the
right.
event horizon, but never from inside. Nothing from inside.
It's never true. Well,
Some people think that it can, right?
Yeah.
I think you get enough physicists in the room, they always find something to disagree. So some people who work on really speculative physics like string theory think that you can get quantum tunneling out of a black hole. So at least some people.
Yeah, I mean, so said your work is in kind of extragalactic astrophysics, supermassive black holes at the center of galaxies. I mean, tell us a bit about your work, about how you even begin to address this question of why it is that galaxies have these massive black holes at the center.
Well, that's an excellent question, and something we're working quite hard to study. As I say, there are different theories for how you can grow black holes that are so big. We know this channel, how to form the small black holes through the stellar evolution process. Now, how do we form the supermassive ones? Well, a theory is that you just take small ones and you make them collide with each other and you merge them, and over time you grow them. So that would be a way. There's a problem with that. There's the fact that there's this big gap in mass, right? The fact that we don't see any black hole with intermediate masses sort of contradicts that. There's also recent observations that have found some of these supermassive black holes. When we look deep into space, so only a few 100 million years after the Big Bang, you already had some of these supermassive black holes in place. And that's a huge challenge for our theories of how black holes and galaxies form and grow, because that's really not a lot of time to build such a big black hole.
So still a lot we don't understand. I mean, let's bring in Karim and Stephen on this. Questions for Amelie.
So just what you were just saying, really. So when would these kind of early supermassive black holes have formed before galaxies, or just at the same time as galaxies?
Yeah, so there's still, the conditions were all a bit different in the very early universe at the time when the first stars and first galaxies formed. So we think that back then the first stars to form could have grown much bigger than the stars we form in the universe today. So you start with these bigger stars, you can form seed black holes that would be already a bit bigger.
Okay.
And you form enough of those in a small volume of space, something that will become a galaxy, then through gravity they all merge. So there's just about enough time to do it, but it's still quite a challenge, and you need all the conditions to be just perfectly right.
And black holes, so they're very old, but they're not immortal, are they? Because of evaporation, they actually shrink.
Yeah, that's right. Though if you calculate how long it would take for a supermassive black hole to fully evaporate, the number is, well, astronomical, for lack of a better word. But
we also haven't ever observed black holes evaporating. So this is, it might, like most physicists that I talk to seem to think that they definitely do, but we still don't know.
Absolutely.
Can you say something about what that even means? This idea of the black hole evaporating makes it sound like a puddle or something.
So I guess, like, one of the things that's most fascinating and problematic about black holes is that a lot of the properties of the black hole are really not properties of the black hole itself, the properties of this horizon, which is the kind of, you imagine that space-time has two kind of sectors. The sector that you can escape away from the black hole, and the sector where you can't escape. So it's the boundary of the sector where you can't escape from is the horizon, it's the edge of the black hole. And back in 1975 or something like that, Stephen Hawking predicted that there were effects due to quantum physics that meant that you'd expect radiation to come out of the black hole. But what Hawking didn't do is give a simple mechanism for how that radiation actually comes out. So you get these problems. I think you picked up exactly the right question, is how can it radiate if nothing's getting out? And so there's very general mathematical arguments why we should expect it to have a temperature and to lose energy through radiation. But there isn't a clear mechanism about how that loss actually happens. So it's very puzzling, but it's also very fascinating.
But that's typical, isn't it, of where general relativity, which is all the black hole large-scale stuff, and quantum mechanics,
Exactly.
which is the very fine detail of what goes on at the tiniest of scales, at the horizon. They collide, don't they? Because we still haven't got an overarching theory that unites the very big and the very small, even though they're fantastic theories in their own right.
Yeah.
That's right.
So you get these edge effects in a way, which are maybe a hint of the quantum relativity theories that are to come in the future.
One of the reasons people believe in these predictions, like Hawking radiation, so strongly, is that all the different theories of quantum gravity seem to all agree about this stuff. So lots of physicists have different ways of trying to combine, like exactly as Stephen was saying, combine quantum mechanics and relativity theory. There's string theory, which is the most famous. There's also loop quantum gravity. There's other theories that are a bit smaller. But all of them agree pretty much on this temperature thing. So even though there's no direct evidence for it, because all their theories agree, they're like, oh, then it's definitely there.
Yeah.
But we haven't got any evidence for it.
And another place where these theories collide is the singularity,
Exactly.
which you're pretty careful about to mention.
Yeah, well.
But right, my understanding is right at the heart of the black hole.
Yeah.
Einstein's equation, they go off to infinity. So that means the theory's bust, basically.
Yeah,
so
yeah.
Which is a singularity. It's a hole in the equations, essentially.
That's right.
But you're down at a point where the quantum effects must be taking over in some way.
Exactly, and that's a place where, as physicists, we can't really describe that very accurately because we simply lack the tool, we lack the theory to actually do it. So to really explain what happens at the event horizon or at the place of singularity, you almost have to go one way or the other. So that's why it's a very controversial kind of field, because you need to let go of some basic fundamentals of general relativity or quantum mechanics, and you can imagine how people get quite upset about these things.
Fight.
And it's not, like, I just want to emphasize that the problem of the singularity is not just that there's some horrible mathematical problem, it's really a physical problem, because relativity theory actually predicts that things you can measure, observable quantities, would go to infinity, have an infinite magnitude in a finite amount of time. That's what the theory predicts. And that's something I personally think is physically very unsatisfactory. Because you imagine some poor little astronaut measuring something, and their measurement they should be able to read infinity after a finite amount of time. This doesn't seem something we can physically make sense of.
No.
I love this idea of the black hole as a place where the bounds of possibility are stretched, right? And we start to wonder whether what the physics is describing is actually possible or not. And then also this thought about black holes are this place where the physics of the very, very big meets the physics of the very, very small, and we just don't really know how to reconcile them.
Right.
Also a place, it seems, where the boundary between theory and what is actually known from observation is incredibly fluid and unstable. I mean, on this issue of supermassive black holes in the middle of galaxies, What's the status of that? Is that something we really know from data?
Yeah, I think so. I mean, it always depends on how comfortable you are in believing in something that you can't directly see, right?
Yeah.
It's like when you do astrophysics, you have to become comfortable with dark matter or these kinds of things where they're part of the theory, we play with them, it's fine, but you have to kind of trust in the theory and that it's our best model. And so, assuming that we're comfortable with the act of inferring the presence of the black holes, and because all the observations matches with predictions, then in that sense we are quite comfortable in saying that indeed there are supermassive black holes at the centers of most galaxies.
So do you think we're as confident of that as we are that they exist at all?
Well, to me that's a bit the same question, their existence and the evidence for it.
To put Jonathan's question differently, it seems like there's just as good evidence for normal-sized black holes as there is for supermassive black holes. Is that true?
Oh, yeah, absolutely. I would say observations come in different form, but I mean, we have now what's very exciting development over the past years, the ability to not just see black holes, but to almost listen to their collisions through gravitational waves. And that's something that is bringing a completely different way of gathering information about black holes. So we've picked up with these gravitational wave detectors the collisions of black holes. And again, it's another prediction of general relativity. Then if you have a collision of two supermassive black holes, you predict these ripples in space, and we're being able to pick up with that. So,
This is the
with
massive
all these,
thing in Antarctica.
No, this is the experiment called LIGO. It's 2 stations in the United States at the moment. And with all these things, right, if you have multiple lines of evidence towards something that are kind of orthogonal to each other and they all converge into the same evidence, then your faith in the results kind of grows.
I have this image of listening to the black holes, as in the sense that the evidence is in the form of these gravity waves.
Absolutely. So you're really...
Yeah, well, I did read that I may be wrong, but the frequencies are actually sonic frequencies. So you can listen.
You can actually listen to it.
It's a chirp,
yeah.
like that. Yeah. That was just me, by the way. Don't don't evacuate the room now.
It wasn't a black hole. Yeah. Great. So it'd be fantastic at this point to take 2 or 3 questions from the audience on this topic of what a black hole is, and Amelie's work in understanding how these black holes at the centre of galaxies affect how galaxies evolve. So the question from the back there. There'll be other opportunities later to ask questions too.
Thank you. On the question about the evidence for black holes, I mean, it's clear that there is observational evidence for the fact that something like an event horizon exists. But some type of black holes, in my understanding, we have also claims from theory about their inner workings. So if you take a look at, for instance, a Kerr-Newman solution, a slowly rotating charged black hole, you also have claims about what happens in the inner event horizon, not just the outer event horizon. Do you think we have also evidence for supporting the inner workings, the theoretical predictions about the inner workings of black holes?
Yeah. So I think this brings up an interesting point about black holes, is that they are relatively simple. So one of the basic predictions, something that's called the no-hair theorem or the no-hair conjuncture, which pretty much has that black hole have 3 parameters that describe them: their mass, their spin, how fast they're rotating, and their electric charge. And that's all that we can measure. So if a black hole grows by gathering all sorts of different stuff, you lose completely the information about this. And that's a problem in the quantum mechanics context, because there's some information about particles that you're not allowed to lose, but black holes allow you to lose. So if we believe that theorem or that posit, which so far all evidence points to that means that there's very little we can know from the outside about the inner workings of the black hole beyond these 3 simple quantities, which is pretty much just how much mass there is and how much spin they have. The charge, we don't really believe that charged black holes would actually exist. So it's really down to these 2 parameters. So in terms of using external observations to figure out the inner working of the black hole, we're quite limited.
And time for one more question. There's a question from over there.
Cool, thank you. I'm a neuroscientist, not a physicist, so just bear with me for a second. My question relates, so if, according to general relativity, your perception of time will change as you get nearer the black hole and closer to the singularity, so time will slow down progressively. So is it that what we're seeing from the outside, our experience of the black hole from the outside, is it the slow, the slow motion collapse of whatever it is collapsing? And if you were in the black hole, everything would happen infinitely fast, and what we're seeing is a process just very slowed very, 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 very slowly.
Yeah, I mean, that's an interesting thing. We've been talking about this, the event horizon, this sort of point of last return, at least when it comes to light. If you, again, in the general relativity context, if there's nothing special about that boundary, so if you were an astronaut on a spaceship and you were to cross into the event horizon, you would notice absolutely nothing. There's nothing special or particular about that specific point in space. But for an external observer, we would never see the astronaut, cross into the black hole. So that perception of time stretch would be perceived by a distant observer rather than by the person himself or herself falling into the black hole.
So what does the distant observer see? They never reach the...
No, you would see the person slowly and slowly getting closer and closer, and time would stretch. And then there's all sorts of effects that on light. So light changes wavelength, so the astronaut would appear redder, and then he would dim, or she would dim, and then eventually disappear.
And you'd never see anything more of them. From their point of view, everything's carrying on as normal.
That's right. Unless they've been ripped apart, but that's a different matter.
Okay, yeah. I mean, let's turn to this issue then, and come to you, Karim. I mean, let's kind of go on a sort of imaginary journey into a black hole then. I mean, what do you think happens at the edge of the event horizon?
So I guess one of the really interesting questions, right, is how can we learn about this event horizon without actually going through it?
Yeah.
Right? So even if we could send, there aren't any local black holes, and even if there were, I think there'll be ethical implications.
That's good, right?
Yeah. I think even if there were, there'd be ethical implications in sending a manned mission inside one. But even if we got ethics approval and did it, they couldn't send us a signal back. And so one of the things that I'm really interested in as a philosopher is a kind of program to learn about, particularly the horizons. I think there isn't really a way of learning about the singularity this way, but people have been trying to learn about the physics of the horizons by using analog horizons. And so what this is in a sense using the analogy between light and sound. And what you can do is create a fluid flow. If you imagine a bathtub, you imagine a really, really quick fluid flowing down a bathtub. You can get the fluid to flow fast enough, or if you can get the fluid to flow fast enough, that it's flowing faster than the speed of sound. Then if you imagine, rather than an astronaut, we imagine a fish that can only communicate by sound. That'll be a lot like our project of sending someone in. As they cross the horizon, their last kind of cry of help would get the equivalent of its colour changing, which its pitch would change. And they would then kind of go past the horizon. But of course, because we're doing this with sound, we can look on both sides. We can start doing physics of these sonic horizons. And this is stuff that people have done in a slightly different way. There's a recent experiment in Israel where people created, using something a bit like a fluid, but it's slightly different. It's like a superfluid almost. And they created one of these horizons, and they started testing some of these strange predictions, like there being a temperature. So I think it's going to be very difficult for us to get direct experimental evidence for things like. But bear in mind, this temperature that we're talking about is not a temperature that Amelie's going to pick up on her instruments. It's billions of times smaller than even the echo of the Big Bang. It's tiny, tiny, tiny fractions of a fraction of a Kelvin. So they're so cold that we're never going to be able to measure their temperature. So doing these kind of analog things is one of the ways that some scientists at least think that they can learn about them by proxy.
you say more about this idea of an analog here? That this is using water, trying to create a black hole with water.
In practice, they don't use water. They use special kind of very, very exotic things called Bose-Einstein condensates, which is a little bit like a superfluid, although it's slightly different. So they're actually using quantum theory to describe this.
That would help if I knew what a superfluid was.
So they're kind of really fluids that flow very, very flow very fast, and can be described very simply. But you can the original idea came from actually using water, and so the maths works out very similarly. So you can really imagine it. It actually came. The very, very original idea came from just a waterfall. If you imagine as water's flowing faster and faster and faster, it starts flowing faster than the speed of sound in the water. So once you've gone past the horizon where the water's flowing faster than the speed of the sound in the water, if you try and send a sound signal back through the horizon, it will get washed down. And so the idea is that you can use this kind of real physics of the horizon to, in a sense, simulate the physics of a black hole.
So you can create a kind of hole that no sound can escape.
So it's called a dumb hole.
And then try and understand a black hole from which no light can escape.
Exactly.
And what sort of things can be learned from doing this?
So the simplest thing is that it could have been that they created this analog black hole, this dumb hole, and not found the temperature. Of course, this isn't a real temperature. This is now a sound temperature, so it's slightly a bit strange. But if they had not found, at least what I think is reasonable to say is that if they had not found Hawking radiation from a sonic black hole, we'd be rationally justified in being less confident that there's Hawking radiation in a real black hole. So it's not a kind of all or nothing thing, but I think we can learn a little bit. We can rationally change what we should believe about black holes by doing the analog experiments.
And Amelie, I'd love to hear what you think about this. I mean, Karim is essentially saying we can find out what happens at the edge of black holes using liquids, water. You use telescopes and look at very distant objects in the sky. Is this going to work?
Well, for some things, clearly you can't. Like you said, I don't think you can reproduce the physics of the singularity in an experiment like this. But just to
all the collapse, right? It's not like these aren't formed by a collapse like a black hole. You engineer them.
No, but to test some ideas, and again, I don't think you will be able to prove or disprove anything, but as you say, to add some evidence that, again, in our picture of let's try to come at a problem from different angles and all see what builds up, that's definitely a very viable approach.
So can you test ideas like Hawking evaporation then with these models?
So not the evaporation, because you don't have the kind of process of mass being lost in the same way. So you get the radiation. I don't think, to my knowledge, that people have got a kind of dynamical process of actually losing the analog of mass. Because in a sense, what this isn't really a black hole, it's just a horizon.
Yeah.
So you don't really have mass for it to lose.
Yeah, I mean, it's fascinating, this thought that we can't create a black hole on Earth, but we can create something with some of the properties of a black hole.
There were some people who thought that you could create black holes, and they were saying that you might be able to get them out of the LHC. So I think everyone's quite glad that turned out to be false.
So by colliding particles violently enough, they'd collapse.
I think it was a small, you'll know better than I, but a small minority who thought that might happen.
I mean, this sort of gets us into this whole topic of where the physics of black holes merges with the kind of philosophy of black holes in a way, because there's something pretty philosophical about this.
Sure.
These analog experiments with water, right? This inference. Amelie talked about inferences, the inferences we can make about black holes by looking at their effects on the things immediately surrounding them. This is a whole new kind of inference where we're not looking at what's actually surrounding the black hole, but looking at something completely different.
So I think it's similar to some inferences that, like for instance, if you think like a very simple example is using a little model aeroplane in a wind tunnel. We think we can learn about real aeroplanes that way. So, moreover, like using a computer simulation, we think we can learn about a physical process. in the end, the problem is we've got to know what that our simulation has the relevant similarities to the thing that we're trying to learn about.
Yeah.
And checking that in the model aeroplane, we've got good physics to do that. In the computer simulation, sometimes it goes wrong, but I think physicists or scientists know how to do this. When it comes to these kind of really exotic simulations, I think there's reason to be a bit more cautious that the inference from the fluid to the black hole is something we might not understand fully. So I think there are places where we use these kind of analogies in a really reliable way. I'm not sure this is necessarily one, but...
But you don't know until you try.
I'm curious to hear from the philosophical point of view, this whole idea of accepting that black hole exists from this evidence, which is slightly indirect. Is that something that's...
So I think, one thing I think is really useful for me as a philosopher to think about things is having this kind of granuated degrees of belief. And so people talk about this as in terms of Bayesianism or credence, and the idea is that you can kind of have a probability in something. And so stuff like inferences to the black holes existing, it seems like if we ask some physicists, how much would you bet that black holes exist, or something like that, they're going to give you, what would you say a fair odds were? They're going to say, I don't know, 95%, 99%. If you start asking them, what would you say that the horizon has a temperature, maybe they're going to go down a lot. They're going to say 50%, 60%. If they start asking them about what happens at the singularity, I think anyone who says more than 1% is very, very brave.
Yeah.
So the singularity is what, the centre?
Yeah, exactly.
So there's one really crazy idea that's very, very speculative, is that you could actually get at the singularity, it could turn into a time-reversed black hole and then be they're called a white hole.
With energy spewing out as opposed to getting sucked in.
But you say speculative, there's no evidence of white holes?
No. Sorry to disappoint. No.
It would be quite exciting if there were. But the physicists who argue for this do it using mathematical models. They're well-respected physicists, and it really at that point does go into science fiction. When you think about it, like a black hole, a white hole is actually something that's kind of you can't. I'll get the wrong way around. How would you describe a white hole? You can't. Nothing can get in. Nothing can get in.
It's just, it has a horizon in the same way.
And matter comes out and nothing can get in.
I suppose it's always been true in the history of science that there are always things that we believe in but can't see yet.
Sure.
Atoms. You've got a great theory based on the macro level effects of atoms existing even before you see them. So I suppose there are always going to be boundaries like that beyond which you can't actually see yet. But going back to singularities, though, there are models, aren't there, of naked singularities. When you have a very fast-spinning black hole, object, I think, tries to collapse into a black hole, it becomes a kind of donut with a rip in space in the middle, which is exposed, not neatly hidden by a singularity, by a event horizon.
Yeah, that's one of those. When I was talking about the properties of black holes, there's some that can be spinning, and that if you solve the equation of general relativity for that, you find that the singularity is indeed a rotating a ring, and then what happens at the center of that opens the door to all sorts of portals into
horror,
different places.
And just because obviously I really like the analog experiments, can you guess what the analog experiment for spinning black hole is? It's a whirlpool. And so there's this wonderful physicist called Silke Weinfurtner who's actually built a large fluid tank with a vortex in it to simulate the spinning black hole.
So we've had the hot tub time machine, right? We've got the hot tub black hole. I want to go to that resort. That's fantastic.
So what about wormholes, right? White holes, the idea is constantly spewing out matter. There's this, sci-fi notion of a wormhole. You go in one side, you come out somewhere else. Is there a basis in physics for this?
Well, that's where it gets. I wouldn't want to put the hat of science and proclaim anything here, but
it's okay, you can take off the hat of science.
Yeah, I mean, it is in principle allowed, right? Some very serious physicists have made predictions for these things. And it comes down to the fact that, again, we're limited by the tools we have, right? It's that point where GR, general relativity, quantum mechanics, all of that. So that gives you a bit of leeway to come up with all sorts of different theories.
So is this in the same category as the white holes? Some serious predictions?
Absolutely.
But it involves the
no
white
evidence.
holes.
Yeah.
So the wormhole really
It's
is
the
a
other-
black hole and a white hole connected together by a tube.
Yeah, and it's a tube outside normal space-time, so it's like a shortcut, you know. And I think the physicist's problem with it is that you need an exotic kind of matter to hold this thing open, a kind of anti-gravity field, and no one's quite sure are they how to make this stuff. But if that exists, then you can hold this thing open and possibly pass information through, or even objects through.
But only one way.
Well.
So you wouldn't be able to get back, presumably.
No.
No, true, fair enough.
So Amelie, I mean, if we can tempt you to take the science hat off for a moment, what's your speculation about what is happening inside a black hole? What do you think?
Well, if you define black hole by inside the event horizon,
Yeah.
there's nothing special about it until you get to the point of the singularity. It's
And what do you think happens there?
at the singularity.
In the movie Interstellar, right? The guy sort of goes and finds his son or something. What? Presumably that's not very daughter. Presumably that's not regarded as a serious hypothesis by physicists. What sort of possibilities do physicists take seriously here?
Well, first of all, I mean, in terms of movies, Interstellar did quite a lot of work with, very, very serious physicists. So I wouldn't, dismiss out anything in there just because it is the stuff of movies. It's actually where movies go that it is quite well grounded in actual science. But yeah, I mean, from my perspective, it's probably where that's the difference between the philosopher and the scientist. For me, it's almost, from where I stand, my interest in black holes and evolution of galaxies, it's almost pointless to think about what happens.
An analogy, a different type of analogy. So there's another part of physics where we deal with things very much like the singularities in black holes, and that's the early universe. So the other place where we think that there's the equation of general relativity lead to a singularity is right at the Big Bang, right? And so, in a sense, that's why it's such a big problem for us to try and start saying things about what happens at the singularity. Because if we knew what happens in black hole singularities, we'd have a lot more understanding also of what happens at the beginning of time. So it's really, really a fundamental question. That's why it's so exciting, but also why it's so difficult to speculate. And it's very hard. It's very hard for us to learn about the very, very early universe. So it's kind of something that's really interesting could happen there, but it's very difficult for us to find out.
But it's as well that thinking that with the proper tool, with a theory that encompasses quantum mechanics and gravity, it probably wouldn't be a singularity as well. So
one idea would be that if we learn about the singularity at the beginning of the universe, so some models, there isn't a singularity, they call it a bounce. And so there's actually would have been a whole nother universe, and the universe kind of collapses down and expands again. And so that could have been what happened at the beginning of time. If we knew more about those kind of theories, we might be able to speculate more kind of robustly about what happens in a big...
So there could have been another universe before this one.
Opposite time.
So some of the biggest, hardest questions in physics essentially raised by black holes.
It's definitely a place where things break down, so that allows for all sorts of theories and speculations.
Like the Big Bang, right, where the physics of the very big meets the physics of the very small. It'd be great to take a few more questions from the audience on any of the issues raised so far about what black holes are and how we can begin to speculate or theorize about what might happen at the edge or inside. Let's first of all go to the front row, and then we'll go back to the back row.
Talking about the immense size of these super black holes that are maybe formed 13 billion years ago, wasn't the cosmos much more dense at that time. The material density and the energy density just so much greater. And how do we know what those black holes look like today?
Well, to know what those specific black holes look like today, we just have to look in the universe around us. The universe. So the fundamental principle of cosmology is that there's no preferred place in space. The universe is the same everywhere. So when we look very far back, in the distant universe, we're in some sense seeing back in time because of this speed of light, the travel time. But by the time we get the light here, that bit of the universe over there has evolved just in the same way our bit of the universe has. So the supermassive black hole we see back then probably has evolved into something that we can see around us in the universe today. So we can find analogues for these objects in the universe today.
And a question from the very back row there. Please wait for the microphone to come to you.
So my question is more on the science fiction side. I think you said, Mr. Thébault, earlier that at the singularity of the black hole, there is a possibility of time travel. And I've read something that because the black hole always saves the information it swallows, and if you could recreate the spin of a black hole and spin it out somehow, you could recreate what once went into the black hole itself. And if that would be a person, this person would travel through time. I mean, obviously it would be dead by then, but I just wanted to hear your thoughts on that.
I don't know how I want to take this one. Well, I think just for the science bit, that is a fundamental problem with black holes, is that they swallow information. We lose information. When stuff goes in, we lose any information other than its mass, pretty much, which is a big problem. And that has led to all sorts of debates about whether we can get that information back. And there's some modern theories that say you can get some information back, but it will be in a way that's almost impossible to recognize. So you couldn't just turn back the clock and read exactly and recover exactly. You can get information back, but in a sort of garbled kind of a way.
But there is a way to use a wormhole as a time machine, as I used in one of my Xeelee novels up there. And I think it was Kip Thorne, one of those guys. So a wormhole, you in one end and out the other in space. So to turn it into a time machine, you build a wormhole with two portals quite close together, orbiting Jupiter, say. You take one of them and fire it off on an interstellar ship for 100 years, somewhere close to the speed of light, and then back again. The twin paradox, about that, were if you do that with a pair of astronauts, twins, one stays on Earth, one is on the ship. The one on the ship comes back much younger than the one on time dilation. So with the wormhole portals, they're the twins. So you've got a younger one and an older one. Bring it back, so you've got the one from 2000 AD, one from 3000 AD. You can use it as a time portal as opposed to a space portal by combining those effects of the bending of space-time and time dilation. So,
that's really clever.
Yeah, it's all fabulously speculative, but that's a way to use it as a. But
I think it would. I'm not sure, but surely if it's a white hole or a black hole, it means you could kind of go one way, but you couldn't. Could you go back again?
In a wormhole, you can.
Okay, you can go back and forth.
Yeah.
Because you wouldn't want to go to the distant future and then not be able to get back, would you?
No. It's yeah. But that's the point I was saying about the anti-gravity frames that hold the mouth of the thing open, so you're not crushed as if falling into an event horizon.
Oh, okay.
You can survive on some finite scale and go through.
That's amazing.
Yeah. So if you've got anti-gravity, then you've got a time machine.
Easy.
To just follow up on the death aspect of the question, right? I mean, is it that inevitably anyone who goes inside a black hole dies horribly, or do they just live a normal lifespan and then die of old age?
Yeah, I think you will die horribly. The question is, how quickly will you die? And from what, if we want to go. I mean, a small black hole will kill you quicker than a supermassive black hole. So if you want to, for a supermassive black hole, you can actually penetrate into the event horizon and you'll be fine for a little while. whereas the small black holes, the field, we call them tidal forces, very much like the Earth and the Moon and being stretched.
Water analogy again.
Yeah, so you could, yeah, exactly. Small black holes would rip you apart before you actually get to the event horizon.
And they rip stars apart, right? That's one of the reasons we see them. Is this true?
Yeah, well, yes, so that's some of the evidence we have for these black holes. It's mostly when stars are in what are called binary systems, two stars orbiting each other, and one of the star is a black hole, has become a black hole, and then it can sort of swallow material from its companion stars, and that material sort of orbits around the black hole, gets really, really hot, and that emits X-ray radiation, for example, which we can then detect.
Isn't there some evidence of that with the supermassive black hole in the centre of the galaxy with what looked like broken up stars?
Yeah, well, we're trying to, that was a discovery from just a few months ago. We can witness clouds of gas going in orbit around, not very far, just a little bit further out from the event horizon. So there is definitely material there that the black hole can swallow.
And time for one more question on the physics and philosophy of black holes.
It seems to me that theoretical physics is approaching a point where we are developing ideas and theories that are not directly empirically able to be tested empirically. And I wanted to ask you, do you think that in the future we will have to devise some kind of way to decide between theories from a theoretical point of view? So in other words, is empirical evidence going to be less significant for future theories?
So lots of philosophers have got very excited about this recently. Unsurprisingly, as with most debates, some of them think definitely, in a sense, we need to learn new tools to assess theories without empirical evidence. One of these ideas is using, it's called the no alternatives argument. If you look very hard for alternative theories and you can't find any, that's evidence in favour of the one you found. Other philosophers are very, very unhappy about this, and I think this is a kind of a negative and pessimistic and potentially damaging thing to happen to science. So my personal view is that in the past people have always said, oh, we won't find any, we've kind of reached the end of our horizon, and they've been wrong, and I hope that's true as well. But yeah, so I'm very hopeful that new evidence will, in our lifetimes will help to decisively change these things. But certainly some philosophers think that the scientific method will change such that we should be able to assess theories without evidence.
Well, Amelie?
Yeah, well, I was going to say, that is the fundamental principle of the scientific method that we've built over thousands of years, that you make predictions which you confirm with experiments, or sometimes the experiments are ahead and in the waiting for a theory to explain them. And it's always been like this. It's been this interplay of the two sides pushing each other forward. So for me, as somebody who works in the realm of observations, it's quite difficult to think of theories that can be self-fulfilling in some sense, but and that's why string theory, while a very credible theory, is not very mainstream for that reason, that it lacks the ability to make predictions that we can verify at the moment.
One of the predictions that the string theorists are most happy about, that's seen as by some people seen as evidence for string theory, is exactly the prediction about the temperature of black holes that we were talking about. So this is a strange situation, that the prediction that you have a temperature for a black hole is a very speculative prediction. But even recovering that is seen as a piece of evidence in favour of string theory, and there's no empirical evidence.
So just generating a prediction is seen as evidence?
That we get from other parts of physics.
Right, whether it's confirmed or not.
Yeah, so it's consistency between Hawking's prediction and theory of quantum gravity has seemed like a litmus test. Well, the litmus test is just being consistent with another theoretical prediction we haven't empirically confirmed.
Amelie, do you think this is the end of science? If theories are no longer being tested against data but against other theories?
No, like I said, it's more a revolution in the way we do science, but that's not
So
the end of things.
my big hope is, like I said before, I think there's chance, it's unlikely we'll know things about Hawking temperature or inside of black holes probably ever, but it's very likely or very possible that we could learn about the early universe, and we might be able to use observations about the early universe to test our theories of black holes. So that's a possibility.
Yeah, so more time for questions later, but for now, I mean, let's think about this point where knowledge ends and fiction begins. I mean, you're noted for a kind of sci-fi that involves taking physics very, very seriously, being very, very informed by current science. The science of black holes has been very fertile ground for you.
Well, yes, and I think since the idea of a black hole coalesced, was the 60s, I guess, language like event horizons and so on. The science fiction writers picked up on the possibilities, and I would say the first great black hole novel was Gateway by a writer called Fred Pohl, which is Pohl, from 77, I think, something like that, called Gateway. And he picks up on the situation you described so well about a big black hole, you've got an astronaut falling into it. I think in this story, she falls through the event horizon feeling nothing, but she's doomed to die in some finite time, isn't she, from her point of view, by falling in. I think it's inevitable, isn't it, watching through the event horizon, you're going to go into the singularity.
That's right.
You can't get back out again. Or, well, you can't even extend your time. You're going in there, down the plug hole, in your model terms. But as you said, an external observer, from their point of view, it's his point of view in this case, you see the astronaut kind of plastered on the event horizon like a fly in amber. So in fiction, that's a great scenario, but it's the question to ask if you're trying to generate a piece of fiction is who's it hurting? Who is being hurt by this scenario? And well, the astronaut who's doomed to die in some final time, but also the observer stuck outside, because from their point of view, their loved one is doomed for one thing, but it's still there as a kind of image. It's tantalizing or agonizing that their death will not occur in your lifetime, in a sense, because of this distortion of time at the horizon. And Fred Pohl built a whole series of novels around that basic problem of, you go in there because there are alien artifacts to find near the black hole, but then if you get sucked in too far, then you're lost, but trapped, stuck in the event horizon. So that's the way the fiction writers take it. What can you do with the black hole? How would it hurt you? What kind of stories can you generate?
Right, so the excitement of black holes for you is thinking what happens when humans interact with them and when our kind of evolved emotions and natures confront something that we just cannot understand and is on a scale that is just far beyond what we can comprehend.
More than that, really. It's more like, what is it like to live in a universe with black holes in? There was a wave of fiction after Fred Pohl about using the black holes in some way, particularly microscopic black holes. We mentioned that. If you go to a microscopic, it's like a very compact source of energy. You can throw stuff in. Some goes into the singularity, but a lot of it just gets compressed by the tides, and you get a burst of energy back out again. So Arthur C. Clarke, in a book called In Imperial Earth, which is about a colonized solar system, he uses a black hole drive in there. And it's not much but a black hole that you chuck stuff in, you get a beam of radiation out that shifts you forward. I think it's been proved since then not to be a very good idea, because it would work very well, it wouldn't be very efficient. You don't get a very good exhaust velocity to push you fast, but it's, in principle it's a way. And there's also a waste problem. Suppose you mentioned black hole gets too large, it's absorbed all the mass that you've thrown into it.
Can I just stop you there? So what Jonathan was talking about earlier seems really relevant what you say. So Arthur C. Clarke came up with the idea. Was it then proved by scientists took it seriously and then wanted to work on showing if it could work or not?
I don't know if Clarke invented it, to be honest. But Clarke was... I worked with him when he was getting towards 90. He was fascinated by the new. The internet was great for him. And he had contacts like you wouldn't believe, like Kip Thorne and people like that, in terms of relativity. So he would have been involved in these conversations. So I think possibly someone was coming up with conceptual ideas and he picked them out. That would work for a starship. So, but yeah.
But there's definitely an interaction between the
Absolutely.
scientists and...
Yeah. But on the larger scale is what I really like about black holes. I think that the fact that they're... It's the geography of black holes, if you like, the fact that the features of the universe, right back to the beginning with the supermassive black holes, well, maybe there were creatures that were some kind of fed off these massive energy sources even back then. And in the far future, and that's what I've got in my Xeelee sequence particularly, what happens in the future, I like to think on these big time scales with lots of zeros at the end. You know, the sun is a star that will last for a few billion years, right? And there's the old joke, isn't there? Somebody said that at some conference, the sun will die in a few billion years, and this guy goes, oh no, don't worry, a billion years is a long time. Oh, I thought you said a million. So a billion is 1,000 million. But what happens in 100 billion years then? Well, there are smaller stars like the Proxima Centauri, the nearest star to the sun, will last trillions of years. Okay, what happens in 100 trillion years then, when all those stars have died off? What will we or some kind of successor intelligence use as structure, as an energy source? And you turn in the end to the black holes. You know, we could all migrate to the supermassive black hole at the centre of the galaxy and do the kind of thing I've talked about, throw stuff in to get energy out. Or you can mine the spin of a black hole for energy, can't you? The Penrose process.
Yeah. So this is actually what the Whirlpool analog model was actually testing, was exactly that.
Yeah. The black hole spinning drags, it's like a kind of paint, I think of it, with a big stick. It drags space-time around with it. So in principle, so it's outside the horizon, right? So you can mine that maybe, and you extract energy, useful energy from that process. All that was shown very well in the Interstellar, in the visuals of the black hole. I think they came up with some new physics actually to show how the light is bent by this swirl of space, and so you see, you know, there's great scenes where you see like a lopsided halo, because the light is being dragged around on one side and pulled back on the other side. You can actually see it if you're standing in front of the thing. It's wonderful.
And Amelie, I mean, is that something that is good for you as a physicist, to see sci-fi authors, filmmakers visualizing this stuff that is so abstract?
Yeah, absolutely. Well, certainly it's useful to have images to put on this, you know, we're talking about Interstellar, but that the realism of this construction of this supermassive black hole, and like Stephen was just saying, I mean, the fact that black holes or high concentrations of mass can bend space and therefore deflect light is something we call gravitational lensing, which is something that we use quite a lot to try to find out about things that we can't see directly. And that's exactly a case where to get that super fantastic detailed illustration, it pushed some of the science further than what we had before.
Yeah. Actually motivated the scientists.
Well, Kip Thornton, this name we keep on mentioning, he served as a science advisor on that movie. And he wrote it's an interesting book. The Science of Interstellar is a good book with nice pictures and everything. But you get the process of how this dialogue emerged between the filmmakers and people like Kip Thorne. I think one thing science fiction does do is ask questions like, well, what does it actually look like then? You know, you have to work out things that aren't necessarily immediately obvious from the theoretical models. But on the other hand, poor old Kip Thorne described a lot of instances where he said, well, if you want time dilation of that much, you've got to be this close. It's just making it. But the filmmakers wanted to be out there, so they stuck it out there. You know.
And part of what sci-fi does is bring the human back into the picture. Right?
Exactly. Yeah.
What would this look like to a human? What would happen to a human?
It also, I think, one of the really interesting things is using the difference that computers make. Like when people first came up with black holes, there weren't powerful computers that you can start studying the kind of. So a lot of the physics of black holes, you need to use computational techniques to really understand them. So, like, I would imagine the fact that they had really powerful computers that they could make the simulations, it was relevant to why the filmmaking was so important for studying black holes. Maybe Amelie knows more about this.
No, well, that's exactly it. In a lot of these kind of extreme physical situations, we're beyond what we can do with pen and paper. Right? It's all down to supercomputers, and the more supercomputing power you throw at it, the more accurate the results you are. So yes, if there's a strong drive to get that accuracy, it will push things forward.
Yeah, at one point in the evolution of science as I've followed it in my lifetime, it looked like black holes might be absolutely essential for our very far future, because there'll be nothing else left. Everything else has evaporated away except the black holes. So Freeman Dyson, that's a name you may have heard of. He's one of these great conceptual thinkers. He tried to prove in a series of papers, in principle, that intelligence could survive almost forever by working on larger and larger scales with more and more exotic objects. And in the end, he had this vision of we'd all work around the supermassive black holes. By that time, the galaxies are all scattered away. But I think it's right to say that the bigger the black hole, the slower the evaporation. So what you need to do is farm them on a universal scale, right? Merge them to get even bigger black holes to make them evaporate slower and last longer. This is all mind, manipulating the universe on a cosmic scale to keep functioning. Fantastic vision. It might not be like that, but I think it's what the mathematicians would call a proof of existence. If there's one way that life and mind can keep on going forever, then there'll be other ways, better ways. However, since then, that's like 20 years ago, since then, dark energy has come along. And the big rip where, this new energy field is just going to smash everything apart anyway, as far as I can see.
Brings out this interesting way in which sci-fi can be a source of optimism, right?
Yeah,
we often think of it as these dystopian futures, but to some extent it's also about showing possible ways for humanity to exist over long time scale.
Oh yeah, I think so. Yeah, and how people can prosper. In fiction you look for conflict and so forth, but you also look for people achieving goals in some way and hope at the end.
I mean, your own novels are often on a time scale that completely boggles the mind. Right? Billions of years. You try to write fiction over the entire history of the universe, and this idea of sort of life in black holes being possible sources of alien life is an important idea for you.
It has been, but I think on the whole I've found the idea of living close and personal to the black hole. I mean, maybe in the earlier stages of the universe's evolution, even the first few minutes of the Big Bang, there were whole epochs where the physics was different, basically, or a different kind of physics was working out. You could get life in there, maybe. So the Xeelee of my title there are from the very early stages of the universe where space-time itself wasn't settled. So you have kind of bird-like creatures of space-time, discontinuities and flaws, surviving to later stages, and that's what the Xeelee are. So later on, they're attracted to the black holes because that's where space-time is twisted and they kind of feed and so forth. In my latest novel, it's called Redemption. One of these Xeelee goes to the black hole at the centre of the galaxy to survive, builds a big ring world around the black hole and spins it at relativistic speeds, extracting energy from the black hole to do so. So, it's a mixture of biology and engineering and what the raw material of it all is. But I do like the idea that in the end, a black hole is nothing but space-time. It's surrounded by its accretion disk, stuff falling in and so forth, but the thing itself is nothing but a flaw in a way of space-time, or a sculpture of space-time.
And Karim, let's bring you in on this. I mean, quite a productive relationship between philosophy and sci-fi, I would say, over the years. I mean, do you, as a philosopher of physics, sometimes look for sci-fi for inspiration?
I was stroke am still a big fan of Red Dwarf. And I don't know, I think for those of us of perhaps, I guess, in their 30s or over, would have seen Red Dwarf on television. And there's one episode in particular, I think, that's really, really philosophically interesting, that actually relates to some of the stuff we've been talking about already, which is called Backwards, in which they go to a universe in which the arrow of time is going the other way. But they, of course, retain their kind of orientation of time. So everything they experience is the time reverse of what you'd expect, with some kind of interesting and humorous consequences. And so I quite like the idea that maybe we can think about possible futures or possible pasts in which our orientation in time is reversed. And so I think that there's lots of really kind of vivid and kind of playful ways to kind of engage with these ideas that kind of cross between science, philosophy, physics, and in a sense they don't really live in any of them.
I think in a more general sense, I think science fiction, modern science fiction, and particularly probably media SF, has actually informed the public view of the universe as a whole, and therefore, the philosophy of the race as a whole. Just the fact that the stars are suns like ours and like space is really big. I think most people know that, if only from Star Trek and so forth. I know it's simplistic with the stars washing past the windows, but just the idea that star is like our sun. It's small and dim because it's so far away.
But it's in the end, it's such an old idea that really the fiction and imagination and art is part of the process of ideas being kind of passed between like scientists or back then natural philosophers or mystics, and there isn't this kind of hermetic seal between artists and scientists and philosophers. And I think, in a sense, what we're talking about is not something particular to sci-fi and physics. There's lots of different ways in which these different aspects of kind of human intellectual life kind of can and should fruitfully engage with each other.
When we're at this stage of where over-specialization and technical knowledge required to do anything is so high that we're forced to dig down onto a little alleyway. But the basics is just what it used to be.
I mean, we've already had this idea that sci-fi authors and filmmakers will often consult scientists to try and get things right. Do you think there should be the opposite too? Authors in residence, things like that, authors in the lab, interacting with scientists.
I mean, we do have artists in residence. That is a thing that we have at times. And absolutely. I mean, some of the hardest questions for us as scientists to answer often come from other realms. And so it's like, I hadn't thought about it that way, at least. And
Well, the idea of wormholes, I think, was consolidated by that kind of person. Carl Sagan wrote Contact. So Sagan was a professional astronomer, rather than but he did write this great SF book, Contact, about first contact with aliens, and he wanted a wormhole as a way for the aliens to reach us and so forth. So he knew. So in relativity, Einstein-Rosen bridges, the idea of these flaws in space-time were already there, but you get crushed by trying to travel through one. So he went to these guys like Kip Thorne and said, is there a way you could make this work then? How do you bend the theory? And I think that's one function of science fiction. It's not so much that you stick rigidly to the laws of physics. You can push it a bit, Well, if I built this, what would you need to make it? A ring world circling the sun would need some material of tensile strength more than we've got at the moment. So how could you build this stuff? Could you use the nuclear force to build a bridge? There's that kind of asking a good question. And the wormhole question was definitely a good question. And back came the model we have now with this kind of anti-gravity field. And masses of papers, as they try to work out the implications of this thing. If billiard balls with wormholes, you've seen those kind of models. You knock a billiard ball down a hole, which is a wormhole mouth, and it pops up over there, knocks itself out of the way before it. It's wonderful stuff. So that's an idea where a concrete science fictional image, really, and science fiction is a very visual medium, fed back a good question to the theorists.
Stephen, in your own fiction, I mean, how important is it to you that what you write is compatible with current physics, or is it to some extent that you will bend the rules? You sort of you want it to be compatible with a kind of hopeful future physics or something like that?
Well, a bit of both, really. I like to try not to contradict anything that's established at the moment, which is tricky, though, with cosmology especially. We seem to have a really good story of the Big Bang. Every so often one decimal point of the age of the universe changes, but the future, as I said, is flapping around like once it was cooling and spreading out with big black holes evaporating. Now it's the big rip where, it's entirely different model. So it's a lot of my books have been invalidated by the science moving on, if you see what I mean. But I've always liked to think that this is credible. This could happen, conceivably, because that's the way you get authenticity in the sense that this could be true. For instance, in one of my novels called Exultant, I tried to map the expansion of humanity across the galaxy, which is something that you see many times in science fiction. You know, the Star Wars throws away the ideas of empires spanning galaxies and so forth. But how do we actually do it, given high-speed travel and so forth and relativity? How would we actually do it? How do we sustain a society which enables us to do these things and so on? So it will probably never happen, but it tests the bounds of the possible in a way, and occasionally going a little over into, well, could it be this way?
Right, and that theme of testing the bounds of the possible, I think, has run through all of your work in very different ways.
I think that's probably, in a sense, why all of us find black holes exciting, is because they're at this kind of edge of what we really know about, and that's what's so exciting about them.
Great. I mean, let's take some more questions from the audience now on this relationship between sci-fi, physics, philosophy, as well as the particular place black holes have in fiction.
Thank you. We discussed early the idea of energy generation from black holes and the huge amount of power that might be able to wield. And we also discussed briefly the idea of bringing humanity back to the far future, the idea of far future science. And I think both of those things are very correct. At the moment, we can wield a very small amount of energy, even compared to the output of the sun. But even that, you look at the last 100 years, has been used to threaten humanity and threaten each other. I guess my question is, are we as humans responsible enough to be even allowed to wield the kinds of power we're talking about when we're discussing energy generation from supermassive black holes?
Well, I think I would say we're probably not responsible enough to do stuff that's far below the level of messing with black holes. For instance, just expanding into space. If we had a thriving interplanetary transport system, the energy that you wield there is huge. The crash of a large spacecraft on the Earth would be far worse than the planes slamming into the Twin Towers, terrorists getting hold of a space plane. The energies that you wield on an interplanetary scale are so large that a war could be, an extinction event. Horrifying to think of. We've managed to sort of keep the lid on the bottle of the genie of atomic power since the Second World War. But it does seem to me, and a lot of other people as well, there's been conferences about this. We really need proper governance on the Earth before we move out into space. Not necessarily a world government, but a decent international order so that war becomes, on any large scale, impossible, inconceivable, just because of so much energy is being wielded. If you think about it, imagine a solar system with a few domed bases on Mars and the Moon and so forth. Well, they will be very easily destroyed, even by a terrorist bomb within the dome. On the other hand, the Moon dwellers could easily chuck down rocks into the Earth's atmosphere, as in Heinlein's The Moon is a Harsh Mistress, and with very little effort, really, and using probably technologies that were built to transfer lunar resources to space colonies and so forth. Fire them at the Earth, and you've got a terrible, terrible dinosaur killer weapon. So really, you're quite right to ask that. I don't think we should. Well, we can't say we're not going to do things. It would be far better if we can expand further our capabilities with a decent governance system on the Earth.
Can I just ask a little follow-up? Because it seems like there's a sense in which a lot of what you're doing that's so fascinating is actually philosophy of social science. So it's like the social science of a future where we had more advanced technology.
Yeah. Oh, I think so. Yeah. But within science fiction, the tradition is a lot of it was American, and a lot of it was rather what you might call libertarian now, the frontier spirit, where Heinlein was the classic case, and he was a pole for American politics for a long time in SF, where you build your colony, but that's the point. Then you move on to the next place, having trashed the environment there. It's this moving edge, out through the solar system and beyond, and you reject violently world governments that would interfere with American politics particularly. So the idea of world governance and so forth, and peace movements, was rather smuggled under the radar by people like Clarke. If you read a lot of Clarke, even in books like Charter Dense, which is about alien invasion, world governments all over the place. He just presents them there. There's a World Council. Everything's. He always makes the point that once you do away with the guns, then all that released wealth and education improves the lot of humanity drastically. So he kind of smuggled it in. Didn't argue strongly most of the time, but he smuggled. He always argued that international communications technology, satellites, would lead to better education, would lead to a united Earth one day. There was a protocol signed by the early telecom satellite operating nations, sometime in the 60s, Intelsat, and he gave a sort of a speech at the end of that, and he said, they sent this article about cooperating in this communication technology, and he said, you just signed the first draft of the Articles of Federation of a United Earth. So he came out of the bunker at that point. So it definitely is. SF writers either have to imagine, how are you going to deal with a war like that, or avoid it altogether. So, yeah.
I mean, those optimistic visions of the 60s, they often seem very much at risk today. Right? It's not clear that international cooperation has been achieved in the way that...
Well, I think I would say, if you think that this is off the topic of us, but I think if you take the long view, it's not bad, really. I mean, global warming, terrible thing, but we do have a global awareness of this thing. It's not like as we were 100 years earlier, let's say. We do have a plan of sorts, don't we, of the Paris protocols and so forth, even if we're not following them very well. There are global governance agencies that are looking at it, even if we're not doing particularly. At least the vision is there. We've got a plan for the year 2100, in a sense. So I take a lot of optimism from that, frankly, that at least the consciousness is raised in most of us, if not all, and there is a plan that we could conceivably follow.
You're so optimistic. It's wonderful. Further questions on any of the topics we've discussed?
Thank you. So you mentioned Interstellar a while ago, and one of the things that fascinated me was the Murphy's Law, which I first heard about in the movie. And at least in the movie, it's presented almost as a scientific law, which is that what can go wrong will go wrong, or what can happen will happen. And to me, it was almost a philosophical postulate. So I was wondering if that law has any relevance when you are speculating about the universe, or what the life of the universe is going to be like.
Murphy's Law.
Murphy's Law. So, what can go wrong will go wrong.
Well,
is that correct?
Yeah, well, I think it connects a bit with what we were discussing earlier about how we want to do science, right? There's something that we call the anthropomorphic principle, which means that if a theory doesn't allow for life to be present on Earth today, then that theory must be wrong, right? So thinking in that way, right? Just considering theories for their future possible consequences and so on. That could be a way to go around the issue of evidence-based science if we're limited in that front. So,
but of course, the problem is we know so little about what are the possible conditions for life. So we're kind of replacing one speculation with another one.
Absolutely, yeah. So
I think maybe the ultimate Murphy's Law, though, would be if, going back to discussions of theories and more and more advanced theories, string theory and so on, what if the ultimate theory of the universe, this mathematical description, is just too hard for our human brains? I don't see why it shouldn't be, really. We may have to wait for some AI to encompass superstring theory or whatever it is and give us the results, which would seem very unsatisfactory. It's rather like computer programs proving Fermat's last theorems, the four-colour theorem is the classic case, isn't it? Where you've got to kind of prove that the program works, but you can actually follow the proof yourself. And it's moving the understanding of the universe away from the human brain in a way. But again, an optimistic note is that Einstein didn't have the maths for relativity, did he, when he started off? You know, he knew that he needed space-time curvature stuff and so forth, and he stopped and studied, as I understand it.
So he didn't know it very well, but a lot of it was established already.
Yeah,
right?
that's
think
true. Yeah.
He certainly was a very good mathematician, but he found it hard going, and he had to get some help in the end.
And he went up to study this stuff, didn't he? And then went back to relativity. So if it's too hard for Einstein.
But Murphy's law, not strictly speaking a law of nature, but maybe a very useful rule of thumb. Any further questions on where physics, philosophy, sci-fi meet.
Lots of questions, but I'll restrict myself to one. On the evaporation thing, at the very beginning, you were talking about Hawking evaporation. I thought there was some sort of, well, perhaps not contradiction in what was said, but unresolved stuff. So we have Hawking evaporation as an idea, and from what Amelie says, we don't know how that works, but we know it. The theory says so, right? And then what Karim said later on was that, well, or perhaps Stephen, that, well, we have the evaporation and the black holes evaporate to nothingness. Well, but you said something about the evaporation actually occurring at the boundary, at the event horizon, and not in the inside. So if the evaporation is only a feature of the event horizon, why would the mass of the black hole decrease to nothingness?
Very good question. So there isn't currently a model of how quantum fields actively, or the quantum-y bit, actively couples to the mass in a process by it. It's very, very speculative. And so all the stuff that people say about black holes, and once the black hole is formed, is for a kind of a stationary black hole that's radiating. And then they just assume that it shrinks a bit, and then radiates some more, then shrinks a bit. But actually providing a full mathematical model in a respectable way that actually describes the shrinking process, to my knowledge at least, hasn't really been done.
So there's a basic, I mean, again, from solving equations about black holes, that the mass and the size are directly proportional. So if you can somehow manage to remove a bit of mass, the black hole will shrink accordingly. So some of these explanation for how the Hawking radiation could proceed is that you think of, little quantum fluctuation right at the event horizon, and then one of the particle escapes, and then the other one gets, incorporated into the black hole. And then if you can think of that particle being incorporating as having some sort of negative mass, you would take away from the black hole, therefore making it shrink. But that's, like I say, the exact mechanics of how that would happen is very...
What's really weird is that it seems that no matter how you try and describe the mechanics of what happens, you end up with the same formula for the temperature, which is why everyone believes in it. So people think that it's kind of a universal thing that black holes have this temperature, even though we don't have a causal story about really what how the shrinking works.
I suppose if the evaporation goes on long enough, the singularity will be exposed?
Well, it will, it will itself disappear.
I guess the size of the horizon will tend towards zero.
Yeah.
So in a sense, the singularity will kind of evaporate, I guess, would be the idea.
Unless you get to a point, I guess, where you've lost enough mass that your light can finally stream out.
But I think that kind of realm is where we get into kind of real speculation. We get to the Planck scale.
I mean, I think it's exciting to think of how much we don't know about black holes and how much there is essentially still to speculate on, still to imagine. But I think the three of you have done a fantastic job of not merely discussing but also exemplifying the productive relationships that do exist and can exist between physics and philosophy and science fiction. I'm afraid that's all we've got time for. Thanks very much for your questions, and let's thank all of our panelists for a really interesting...